So we're carrying on with example 8, which is a ladder problem. Now these things cause a lot of grief and hassle, but just to repeat advice from earlier, don't panic if it's difficult at first, that's because it's difficult, but they all follow the same patterns, so don't worry about it, just get practicing and slowly it will sink in. If you try and do this without lots of practice, you're unlikely to get there. Some people do, some people just have a mind that works that way, but for most people this will take quite a bit of practice. Okay, we've got ladder AB of mass M and length 3A. Have you noticed it doesn't yet tell us if this is a uniform ladder or not, so I can't put my mass in. Okay, so ladder A to B of length 3A has one end A resting on rough horizontal ground, so rough horizontal ground. Now that means that there is a reaction from the ground and there is a friction force. Which way is the friction force going? Well, what's this ladder trying to do? This ladder is trying to slide down a slip like this, isn't it? So the friction force must be acting in this direction. The other end B rests against a smooth vertical wall. Now, if this is resting against a rough horizontal wall, there is a friction force from the wall and there's a reaction force from the wall. The reaction force is going to be going straight out. The friction force would be stopping the ladder falling downwards, so it would be acting upwards. Okay. In some questions they say what is the total reaction from the wall, in which case you take those two components and you combine them into one force vector. In this case though, we've got a smooth wall, so that tells us we can ignore the friction part, it's just the reaction pushing outwards. One thing I'm going to stick in here though is because it came up on an exam paper question for my class this year, and it's a really sneaky way of doing it. We had a similar sort of thing. It wasn't a ladder, it was a beam being held out by a string against a wall, and it was fixed by a smooth pulley here, not a pulley, but a smooth hinge, right? Now, what that means is we can the thing isn't, when you see the word smooth, you think, well, in that case I can ignore the friction. But in this case, of course, it's not just resting against the wall. It's not the wall that's smooth, it's the hinge. So what that means is that when you turn it, there's nothing stopping it turning, but it is fixing this thing in place. So that means that it can provide a force not just straight out, but at any sort of angle that it needs to, because it's kind of pinned in place, all right? So be careful with that. If it's resting against the wall, then the wall's not providing any friction. But if it's pinned to the wall in some sort of way, then, okay, there might not be friction going on if it's pinned smoothly, but the reaction force doesn't have to go straight out from the wall, it can go in different directions. So you deal with that by putting a vertical and horizontal component in, and then working out those two components, and then combining them to give you the resultant reaction force acting out from the wall in whatever direction it goes. Sneaky question, that one, but I've seen it come up, so I thought it was worth mentioning. But on the whole, you tend to have things resting against walls rather than pinned to walls. And if it's a smooth wall, we can ignore the friction on it, so we'll just have a reaction coming out at 90 degrees. Let's keep reading. We've got a total mass of, a load of mass 2m is fixed on the ladder at point C. Okay, now that thing has got a mass pushing downwards. A to C is a length A, so that means this must be 2A because the length of the ladder is 3A. The ladder is a uniform rod, so finally they've told us it's uniform, so I know that that's A, so this distance here is 0.5A, and this is the mass of the rod pushing down from the middle. Ladder is modelled as a uniform rod in a vertical plane perpendicular to the wall. I'll come back to that bit. And it doesn't tell us, it tells us the ladder's got a mass m in the first sentence, so there's mg pulling downwards. I'm going to put in this and this and this and this. The load is modelled as a particle. The ladder is resting in limiting equilibrium at 60 degrees to the ground. So all we've done so far is draw the diagram, and you might be thinking, oh my goodness, all that work for the diagram, but the diagram, I think, is probably at least half of the effort of doing the whole question. That's 60 there, this must be a 30-degree angle here, possible it will need that. I've made my diagram a bit too small here, hopefully it's not too bad. You could always draw yourself a bigger one, and it is very similar to the one in the textbook. So now then, let's just go back to that idea. The ladder is modelled as a uniform rod, fine, but it says in a vertical plane perpendicular to the wall. Now what that means is, we're looking at this thing side on here, aren't we? Now let's look at it the other way, and here's my wall, and here's my ladder. Okay, it's resting against the wall like that. And when it says in a vertical plane, it means if I were to sort of take a slice down here, the whole of the ladder is in the same vertical line. If I had the red ladder resting against the wall like this, then that's not in a vertical, the ladder's not vertical, is it? It's sort of at an angle. So if I put a vertical line down, I don't get the whole of the ladder. And obviously what happens there is the whole situation is a bit different because if I'm, if the wall's pushing here and the ground's pushing here, it's just, all the forces are different. So in order to be able to do these questions at all, we have to have that bit in there. Basically, though, it'll be in every question. The ladder is in a vertical perpendicular plane to the wall. So we'll see that, and we know that we need it for the equations to work, but we don't really have to pay any more attention to it. Finally, what can we do with this? Oh, one other thing I should point out that confuses people, which is this. This is a weight on the ladder, or this could be a person on the ladder, and it could be attached to the ladder, it could be sitting on the ladder. Now, why does the ladder not have a reaction force to this person on it? And the answer is, well, it does, but this person stands on it. Where does the reaction come from? It comes from the floor and it comes from the wall. So because of this force here, these forces will come up differently in our equations, okay? Okay. We need some labels on these forces. They've called this one P in the book, so I'll stick with P. R for reaction from the ground, F for friction, and I think it tells us that this thing here is a mass of 2 kilograms. Is that right? No, a mass of 2m times g. So the weight that we're putting on here is twice as big as the weight of the ladder, or the mass that we're putting on here is twice as big as the mass of the ladder. Finally, we've got everything there. What can we do? We can resolve horizontally and vertically, or if you prefer, perpendicular and parallel to the line of the ladder, and we can take moments. So let's go ahead and do those things. We're static, so the force is balanced. Upwards forces equal downwards forces. What have we got? We've got R going upwards. That one doesn't go upwards or down, that's horizontal, so we ignore that one. This pushes down, this pushes down. So 3mg pushing downwards. This one's horizontal, so we ignore that one as well. So that wasn't too bad. That's actually quite a simple equation for these sorts of questions. Horizontally, there's no acceleration going on, so the forces balance out. There's only 2 horizontal forces, so the friction in the ground is P. Oh, it does say it's in limiting equilibrium, so that's also equal to mu r. We might need to know that one later. So in fact I'm going to put that in as mu r here. Okay, so mu r equals P. Then we're going to take moments. Now I like to take moments about a point where I can picture this thing turning. You could take moments here, you could take moments here. You can take moments here because you can imagine this staying fixed and the ladder sort of lifting up, but I'm going to go for moments here. The other reason for that being useful is because there are 2 forces going through this point, and therefore neither of those 2 forces provide a turning point, a turning effect, okay? You might find that if the force you're trying to find is one of these 2 forces, you need to take moments around a different point, right? So it shows up in the equation, but I'm going to go for taking moments here. And let's hopefully it'll work. You know what, I'll try it. I'm just noticing the book has taken moments about point B. I'm going to try taking moments here, and if it doesn't work, then that'll be a helpful lesson for us. So moments here. We've got this force here, which is going to provide a 60 cos, no it's not, it's going to have a 2mg cos 60 times a moment, okay? Now you can see that as, extend the vertical line of the force, this horizontal distance is 60 cos a, and that force is 2mg, or you can see it as, that distance is a, and the component of the force at 90 degrees is 2mg cos 60. But either way, 2mg cos 60. Sorry, 2mg cos 60 times a. This is 1.5 a times mg cos 60 degrees. And this is, what have we got here? Now, this one, so can you see that both of those are clockwise turning forces? If I held my finger there and I push down, that would make this page turn like that, the clockwise direction. The anti-clockwise moment is a slightly more interesting one. The easiest way to see this one is to go for this way of thinking about it. Extend the line of the force and then look for the perpendicular distance from A to the line of the force. So what's that perpendicular distance there? Well, that perpendicular distance there is the same as this perpendicular distance here, and this is a length of 3A. So it's 3A cos 30, or 3A sine 60 if you prefer. So it's just the height up the wall, right? So that gives us P times 3A, what did I say, sine 60, or if you prefer cos 30, okay? And remember, cos 30 is sine 60. Now let's look at what they want and see if I've got the equations that will do it. If these equations won't do the job, then what I could do is take moments about a different point instead of taking moments about A, and that might help me. Let's see though. Find the coefficient of friction between the ladder and the ground. Well, my coefficient of friction is in here. If I'm going to find it, I'm going to need R. Well, R will come from this equation here, so that's not a problem. I can put that in. And then I'm going to need P. Now, P is going to come from this equation here. And that's fine. I do know everything in that equation there. I think, let's have a look. Now it's interesting. We don't know everything in this equation here, do we? Because we've got an M and an A missing. But look, the A's are in every term in the equation. So I can divide everything by A. And I've just got the M's flying around. Yeah, and actually we've got an M missing there as well. Now, this is an interesting point because often you find that you've got M's flying around and you think, oh, well, how am I going to deal with that? Well, it turns out if you just carry on and ignore the M's, often they'll cancel out, okay? So actually from here, if you've not seen this before, you might look at this and think, well, okay, this whole method doesn't work, does it? I've got three simultaneous equations and I've got R, M, mu and P. That's four unknowns, three simultaneous equations, so we're stuck, but we're not stuck. And I'll do a little bit more maths just to prove to you that we're not stuck. I'm going to take equation 3 and I'm going to divide through by 3 sine 60. So I get 2mg cos 60 over 3 sine 60 plus 3mg cos 60 over 2 times 3 sine 60 equals P. Now that's equation 3. And I'm going to substitute that into equation 2. So substitute 3 into 2, and I get mu. You know what? I'm going to substitute 1 and 3 both into equation 2 at the same time. So instead of an R, I'm going to write 3mg. Mu times 3mg equals P, which is this lot. So that is M. I'm just going to rewrite this a little bit. 2g cos 60 over 3 sine 60 plus M times 3g cos 60 over 6 sine 60. And can you see in this equation here, if I divide this by M, divide this by M, divide this by M, my M just drops out. And the only thing left in this hideous mess that I don't know is now the mu, okay? So this method is always going to work for us. Write down the things that you can do. What can we do? Resolve forces and take moments. But sometimes you're going to find there's an M flying around, right? You've got three equations, you've got four unknowns. But if one of them's an M, don't worry about it. Just keep going. And often the M will disappear. Where the M doesn't disappear, you will find irritatingly that they are perfectly happy to accept answers with an M left in sometimes without giving you any warning of that. But that just seems to be a convention in mechanics that sometimes when they say find the following force, they're perfectly willing to accept the force in terms of M. So leave the mass there. Okay. Sometimes, of course, if you've got four unknowns and three equations, you've missed a piece of information out and you need to use it. But if one of those unknowns is an M, it might be worth just carrying on and seeing if everything turns out nice. And in this case, it does. Good luck with section 7.4. They are tricky questions, but all the techniques that you need are in this example here. So hopefully I've talked through those in enough detail that you can go back and find that bit of information you need when it comes up in the exercise.